Let's appreciate our bit level manipulation, binary arithmetic, and register level device programming by an example of a control loop implemented on an 8-bit microcontroller. This is an electromechanical system in that we're supplying electrical energy into what's called a wire wound resistor. And let's see that live here. So this is, we'll call our plant. That is the device that we are controlling or regulating the surface temperature according to a set point. The feedback point is a thermistor, a negative temperature coefficient thermistor, which we can go into more detail later. That's providing feedback to an analog to digital converter input, which is sampled by our microcontroller, applies logic and a gain, and proceeds to output or modulate the duty cycle of a PWM signal, pulse width modulated signal, and we'll get into that. And what that does is it switches, we call it a low side switch, a power transistor. You may have heard them referred to as field effect transistors, FETs, MOSFETs. This is in that category. And what that is doing is, here we have, if you can see, load power. What's coming in here is a high voltage power supply. It's not powering the logic on the board. It's just supplying the plant power, if you will, the power to the load. It's a 20 volt 6 amp power supply. So when we have this, think of this as a switch, when that switch is open, no current flows. So we're not getting any I squared R loss through our 10 ohm 50 watt resistor. Therefore, we're not generating any internal heat, and we get no heat flow through the body of the resistor, and then therefore no elevated temperature on the surface. When we close that switch, so when we, let's say, assert the line, or when the PWM signal goes high, the switch closes to ground, and then the current will flow, and this will heat up. So that's our closed loop. That's what it looks like on the board. It's a complete system. Every control loop has those elements, and let's see what it looks like on paper, and then we'll look back at the live demo. So here it is, what we just saw physically. There's that power resistor, our thermistor feedback point. The result comes here. We have a reference signal that's coded in our assembly code. It subtracts the feedback. We get an error signal. We apply a proportional gain and some additional logic to condition our PWM duty cycle output. Now, what is PWM? Here we can see live on a scope. This is actually running. This is regulating at present. If we look here, that's 41 degrees C. So the surface of this resistor is indeed warm. 41 degrees C. The room temperature is nominally 25 degrees, and I have a fan running for some forced convection. That assists the demo a little bit, but natural convection suffices as well. More on that later. We can think of it as the operating conditions or disturbances to our closed loop performance. So this is our PWM, pulse width modulated signal, in yellow. In green is our power, our high voltage power supply, as seen at the low side of the resistor, the voltage on the low side of the resistor. So it's reverse. If you want to think about it, if you inverted this, when we open the switch between the resistor and ground, the voltage on the low side of the resistor rises up to, we're 10 volts per division, nominally 20 volts. So we're 20 volts on the input side of the resistor on the high side, and we're 20 volts on the low. We're not putting any current through. When this pulse goes high, our pulse width modulated output, when the pulse goes high, that switching transistor closes the low side of the resistor to ground, and suddenly current rushes through the resistor. The voltage on the low side of the resistor is now just about at ground, subject to the transistor characteristics. It's between the low side of the resistor and ground the transistor is, but we ignore that. We'll treat it as a perfect switch. And what's happening when this green signal is low is we are dumping current into that resistor. This is the heating period, if you will. And we're at steady state. And if we look at our device again, and we turn our temperature probe on. Oh, for reference, this meter is not participating in the feedback. There's a small hole drilled in the case. This is just so we can read a temperature on an independent device. There's a small hole drilled, and there's a thermocouple there, and this low-cost meter is giving us 41 degrees Celsius. So we're regulating at 41 degrees Celsius right now. What I'm going to do next is I have a little air can here, and I'm going to forcibly cool. You can think of this as a disturbance to the system. I'll minimize this video, and we'll look at this oscilloscope. This is live. So the yellow trace represents what's on the orange wire here, and that is what's closing our switch to ground and allowing current to flow through the power resistor. The green trace is on a scope probe just on the far end, on the low side, I'll say the ground side, the low side of the power resistor. That's giving us an indication, really the same information as the PWM duty cycle out, but we're able to see the high voltage power supply on that terminal. So now you can see the scope and the video, and you're going to see a little tube come in, and I'll hit this with some air. And you can see that the temperature is going down, the pulse increased in width, and that's allowing a greater percentage of a period of the pulse width. The duty cycle, can think of it as the percent of the period. The duty cycle went up for a DC signal, we could average it as, if we're looking on the screen right now and we said that yellow was what were 60 microhertz where way you read a scope, we're 20 microseconds per large division. So 20, 40, 60, we're about 62 microseconds, and we're about 8, let's say 10 microseconds, so we're a little over 10% duty cycle. So we could say, we could look at the average power being dissipated within the resistor as 10% of the 20 volt supply, or 2 volts. I squared R loss through the resistor would be, or V squared over R would be 4 over 10 ohms. So some tenths of a watt. And that represents what we're losing to the room. Forced convection. Again, if I hit it with the air gun, I can introduce a fairly rapid deviation. You can see the pulse increase, and then it will regulate back to our set point, which is in degrees Celsius, nominally 40, 41 degrees. There's some imperfections in this loop, more on that later, but this is showing the effect of feedback to process that disturbance and then bring us back to our set point. If I turn off, we can think of the forced convection from a fan I have running as a steady state condition. If I change that condition, we should see the pulse get narrower. We're getting a little hotter already, you see, and the pulse is going down. Now what's going to happen is we're going to increase over our set point. We do not have the ability to cool. So you can think of this as overshoot, but we only can drive one side. We can only put heat in. And now we're reliant on the environment to draw it out of the aluminum block so that our thermistor temperature reduces back below our set point, and then our regulator will start to run again. Contrary to other systems, say like a DC motor where we can drive the voltage positive or negative, we can drive both ways, but here we can only put heat in. If we had a piezoelectric cooler or some other mechanism to cool that block, we could do that. But you can see that by natural convection, that temperature is coming down again, 43 degrees C, 44. If I turn my fan on, it'll bring it down more quickly, and we will start, as you can see, to actively regulate again. So now we're needing to pump energy into that resistor to counteract the convection loss. So we look at it in this form. Our recognizable control loop block diagram. To give a brief introduction of how the assembly code is operating, there's a minimal user interface. So I'll show you that here in the live demo. And that's we can set another set point. So I have an A and a B option. One regulates to nominally 40 degrees C, the other one to 50. And if I type B, I have a console coming in, a console on the computer screen back here. You can barely see it in the video. And that's coming in on this USB port. So the microcontroller is also monitoring traffic, command traffic on this user interface, another element of near every system. So if I type B, I just changed the set point, and you're going to see on the scope that the pulse is wider. Recognize that that's wider. If I go down to A, let me do A again. You see how it's small? As soon as I command B, it knows that I just increased the set point. And now you can see on the thermocouple meter that we're going up 45, 46. We're going to approach 50. And then we'll settle out near 50 again. Of course, if I change back to A, what we just saw earlier, I don't have any way to cool it, so we'll just have to rely on natural convection to bring it back down, and then we would regulate again. So we should settle out near 50 degrees C. So while that's settling, let's look. So we changed the set point. In assembly code, we're taking our thermistor analog to digital conversion result. We're subtracting from our reference that produces an error signal. Now we're performing some low-level bit checks. We saw in our introduction to microcontrollers, an old condition code register was the Motorola name for it. Here we have a status register. We perform the subtraction, then we look at a register that is part of the arithmetic logic unit that indicates the result of our operation. Was it negative? Was it 0? Was there a carry? But in this case, we're saying somewhat practically that, well, if this error came back negative or 0, well, that means if this error is negative or 0, that means that we're hotter than we want to be, and therefore we just zero the duty cycle and basically skip this process. And I can show you that in the code. Otherwise, if this error is positive, that means that the thermistor reading is below our reference. And again, that reading is representative of temperature, so it's below our reference temperature. We're going to apply a proportional gain. We do that with a assembly level multiply command. The 8-bit error by the 8-bit gain. Now this gain is hard-coded, and we won't go into like specific controller design here. This is just to show the overall the performance of the loop and the main components. We can get into the design of it later. We'd have a little more work to do. Interestingly, on a small device, this multiply operation is a 16-bit result in 2 8-bit output registers. So we have to actually look at it as 2 bytes, and it's an interesting little workaround for that. And at this point, we're ready to command. There's one more check. If it looks like a really large error, we just maximize the PWM out, and we drive the amp, close the switch. The PWM then operates as we saw in the scope, closes the transistor, and allows the current to flow through the resistor, and that's how the loop runs. That's our amplifier, as described. If we look here, another view of the same information, but a little more pictorial in terms of that board that you saw in the video. If we look here, we can see now we're regulating to 48. Just jumped over again. Here's the board. We're representing it on, so we're near that high temperature reference. If we look at our scope, we'll see we settled out and we're regulating to that new temperature. Back here to our picture, the logic is represented here as implemented within the device, the analog to digital conversion sample. The thermistor is a very simple circuit. It's nominally 10 kiloohms at 25 degrees C, 10 kiloohms to ground. It's called a negative temperature coefficient, which means as it gets hotter, the resistance goes down, so this value goes up. We're sampling that here. This was discussed. Here's our negative feedback, A or B, based on the user's choice of, or my choice in that example, of set point, negative feedback, application of the proportional gain, and a PWM out, which then, when high, closes this switch, you can think of it as, to ground and allows the current to flow from this independent power supply. So you can see this power supply does nothing but sink current through this resistor when this switch closes. Our PC terminal here is just providing that command. We're also getting the board power supply from the USB cable, 5 volts. And that is then regulated to our logic level voltage, which is 3.3 volts on the board, which is also the reference for our thermistor. As you can see, that 3.3 volts is the high side voltage for this resistive divider here. This LED is just for a little user interface demo. We'll skip that for now. Simplified schematic. As mentioned earlier, if we were going to produce our own product, we could use this as a reference design. This is the entirety of the control loop. And I'll show it. I'll highlight a couple of things. I'll just do it here. There are bit level operations, BTFSC, bit test F, file register F, skip if clear. An example there is, here's our loop running. This is just our demo. This is toggling a bit that we could trigger on a scope to see that we were running, skipping that. Here we're starting an analog to digital conversion. Bit set F is a command. It's a low level machine code, a small, relatively small set, some dozens of them supported by an 8-bit microcontroller such as this. All of your C code compiles into these types of instructions. So a one line in C could be 10 lines here, or 4 or 6. We can later look at compiler output and see how a compiler for a specific family of devices, a specific architecture you call it. This here is a PIC-18 microchip PIC, how that compiler would produce machine code from your recognizable C code. So here's a bit set F. F is the A to D control register 0, and go happens to be the bit. If we looked at the data sheet, we would know that this could be like bit 4 of that register, and that starts a conversion. And now we're polling. We are polling to see if we're done. We could make this interrupt driven, but in this case we're polling, and this loop is running at nominally 60 kilohertz. If we look on a scope, we would see that we are triggering this, toggling this pin up here at nominally 60 kilohertz, which is 4 orders of magnitude faster than you'd need for a thermal system such as this. The time constant of that resistor is many seconds. We can model and analyze that as another exercise, but just know we are insensitive to sampling rate here. We are well oversampled, you would say. When the conversion is complete, the result of the conversion is in 2 registers, high and low. It's a 10-bit A to D, but this is an 8-bit device. So the lower 8 bits and the upper 8 bits are in 2 separate 8-bit registers. Now it turns out that the way that I justified this, skip that detail, but I'm throwing away 2 lower bits, so I'm just doing 8-bit operations here. Assume that we don't want to drive it. Assume that we're hotter than we want to be. Move the part of the ADC result that we want to use into the working register W. Think of it like a mailroom. We've got all these slots, and we're putting something in a slot, and we're getting something from somewhere else, and then we're operating on it with that thing we put in the slot, and then we're doing something else and something else. So you're like a mailroom operator. That's one way to think about low-level programming. And in fact, this is what all your C code, like I said, compiles down to. You start to think about moving data. You're moving data from here, putting it there. And that's what's happening. So I happen to only be using the upper 8 bits of this conversion result, throwing away 2 bits of precision. I'll explain that in another context. Moving it there, here's our subtraction from our reference signal. That's our subtraction from our reference signal is occurring there. That's our subtraction. Here's where we're testing that status register. Was it negative? Yeah, that means we're hotter than we want to be. We just jump right down. And because we had zeroed our duty cycle at the top here, we clear register F, DC out, 0 it. Assume it's 0. If indeed it is hotter or equal to the reference point, then just jump down and move that initialized duty cycle to the duty cycle register. This is move FF. Move file register DC out to file register CCPR2L, which if you read the datasheet for the PWM mode, it would tell you that's how you set the duty cycle. Having checked that we're not hotter, we're now in, let's call it the active region of our controller. We're going to multiply. When we performed our subtraction, the instruction, the assembly code reference would tell us if we put this 0 here, put the result back into our working register W. W is sometimes referred to as an accumulator in other architectures. But again, it's like the scratch pad in our mailroom. We're writing it down, and we're getting something from somewhere else, and we're going and operating on W. Then we're maybe putting that result somewhere else. We're putting something else in W. So W working register is a good way to think of it. It's an 8-bit scratch pad. So we were multiplying W because the error signal is back in W by our gain. The result is in a product high and product low. That is our duty cycle out. We're going to take the high, the low result, the lower 8 bits, and we're going to put it in duty cycle light. Let me do one more check. If for whatever reason that multiply used any part of the higher byte, that would represent a fairly large command in the context of this design. So rather than really operate on 16 bits of gain applied to error, I assumed I only wanted the lower, and then I just check, was there anything set in the high multiply? If there was, just maximize DC, the duty cycle. Meaning we're assuming the error is so large that we need to pump a lot of current into that resistor. And so there'll be instructions like this. Compare W, it's implied that we're comparing the contents of W, move literal to W. Compare with file register F, prod high. Skip if equal. So what this is saying is, indeed, if the if we have zeros in the higher byte of our product, we do not want to just assume to maximize the duty cycle. We want to go with consider maybe the linear region of our controller, for lack of a better term, with the result of in the lower register, which was the gain multiplied by the error. And that's it. And then we write that duty cycle out. And we're doing this, like I said, at 60 kilohertz. So when we observe our oscilloscope, we are modulating that, or we are moderating that at 60,000 times a second. We're checking if we need to adjust that pulse width. Looking back on our video, if we confirm where we're at here, we close out our demo. Yeah, we were regulating to our higher set point, 118 degrees Fahrenheit or 48 degrees Fahrenheit, and we could switch back to A, and again we will see when we switch, when I type A in the control terminal, we just stop triggering on our scope. We're hotter than we want to be, and that means that this condition in our assembly code, the subtraction from our reference signal, is negative. So we go to duty out, and duty out writes we had cleared the duty cycle. That's a 0. That's basically we set it to 0. We cleared it. So think of it in programming where we're doing the variable assignments. We're talking about it here as manipulating the memory location, clearing the memory location. We didn't set it equal to something. And it's an interesting discipline when you take the time to program in assembly to sort of think of the computer in this way, and that can help you because all C code compiles down to this. You may even debug systems where you're looking at, it's called memory dumps or a trace, and you'll see these instructions if the symbols are there in the tool, and you may actually debug a real sticky problem by observing what's happening at this level of instruction. Again, many of these commands or lines of assembly code would represent one line of the simplest C code. So now we are coming back down, and we had our fan running, and we can see on our meter that we're regulating back at 41 degrees C, and again we're triggering on the scope, which means we cooled down, and we have again entered this region. We'll look at the scope. I'll put a little real cold on here, and you can see that pulse go up, and then we'll bring it back. So that is a complete electromechanical system. The mechanical phenomenon that we are controlling is the surface temperature, and we are using a power resistor as our heat source. And we've closed the loop in assembly at a very low level with a microcontroller. We've really got every element of a control system implemented here. If we were to look at our design to close, next steps for this would be to model this and understand its time constant. That's an important closing point, though. Very little modeling was done here. We will have a problem with steady state error, it's called, in this setup. And that's where we'd introduce the notion of integral control, and we'll get to that later. But for now, the structure and all the elements of an electromechanical real-time control system are represented here in this demo.